Okay, so let's talk heat. All right, so heat. Let's go back to our conservation of energy issue. All right, this is what we just learned, right? So the external work is equal to all this stuff from the isolated system. So change in potential energy, change in kinetic energy, and thermal energy, which up until now has really just meant friction. Okay, but what happens with friction? What do you get? Heat. Okay, so it turns out, so this is any external force acting on the system. Okay, so once you define the boundaries of your system, anything coming in from the outside. This is any change in height or stretching of a spring. Okay, this is any change in speed or rotational speed, and this is any change in thermal energy. Now remember, what is this made up of? No, so microscopic forces and energies, right? So this is made up of microscopic potential energy and microscopic kinetic energy. So for instance, thermal energy, if it's heat, that's because the molecules are moving faster. That's microscopic kinetic energy, okay? You can also store thermal energy in like the springs, which are the bonds of atoms, okay? That's a kind of potential energy that can be included in thermal energy. So we have all these things, okay? Yes?
For thermal energy, why is it's changing thermal energy, but why is there no delta?
Oh, that's just a stupid notational thing. You can write a delta. Sometimes they write a delta. Sometimes they don't write a delta. And it's mostly just to confuse you. Yeah. Anyway, how do we measure change in thermal energy? Guesses? Temperature. Temperature. That's the only thing we really measure, right? It's hard to measure energy. How do you measure energy? Do you have an energy meter? No, but we have a thermometer. Thermometer? Thermometer. It measures temperature. Okay? So there's certain things that are easier to measure. If we want to know about the thermal energy, we measure the temperature. So temperature and thermal energy are linearly related. If temperature goes up, thermal energy goes up. If temperature goes down, thermal energy goes down. Okay? And we'll talk about the exact relationship later, but you can assume that they're related. Yes?
Isn't that why it's in joules? Because isn't a joule the amount of energy it takes, or the amount of heat it takes to heat up 1 calorie of water? Joules per gram.
Mm-hmm. But it's not very easy to measure energy. It's pretty easy to measure temperature. You could probably do it with your phone right now, but your phone doesn't have like a joule meter, because like do you know how we get? Do you know how we get? Do you know how we get calories for food?
Calories from food?
No, like how do we measure how many calories are in a food? Yeah, you just light it on fire, and you measure the temperature difference.
Somebody just like cooked up a steak. All right, now let me just keep it on the grill.
Let's see how many calories this is. Yeah. No, but you put it in. You put it in an isolated system. So you put it in an insulated container, burn it, incinerate it, and you'd measure the temperature change. Yeah, that's it. Actually, if you just Google like burning, we'll just light some gummy bears on fire, then you'll realize that so many calories in sugar.
Do they cook it first and then do it? Because
yeah, because if you like go to that stupid Live Strong app or any of those food apps, there's different calorie counts for cooked and uncooked vegetables.
I know, that's what I was saying. Can you imagine being that asshole chef who's like working for like 6 hours a day making all this food?
I don't think.
He walks into the room and they're just lighting it on fire. It's like, what the fuck?
I think it's just like one lab that does like everything. But whatever. Okay, so anyway, if you want to measure thermal energy, I'm glad that you're really excited about this. If you want to measure thermal energy, temperature. Okay? So if you want to know if the temperature is changing, measure the temperature. Sorry, the thermal energy is changing. Measure the temperature. Okay? Work external means you have some external force. So in this case, we have this insulated container with this really weird, this is clearly a contraption from like the 1870s, okay? But it is actually an experiment that somebody did. So it turns out if you really well insulate water and you stir it, what happens to it? It gets hotter, yeah. So when you stir your hot coffee normally, why does it cool down? Yeah, you have the top open, right? You can't really cool the coffee down with the top closed. So you open the top, you stir it, and that's actually just allowing more contact between the fast-moving molecules and they evaporate, and then you get cooler coffee, okay? Evaporative cooling. But if you insulated the coffee and then stirred it, you can actually make it hotter, all right? Yeah, no, hot. All right? So anyway, if this is considered your system and the boundaries are this little thermos thing, right, you have some external work being done on the system. Is there any potential energy? So change in height, or is there a spring? Are those in your system? No. So no potential energy. No real kinetic energy. Okay, at least not on the macroscopic scale, because if you're talking about the motion of the water molecules, that counts as microscopic. Okay. Yeah, like just bear with me here. Okay, so we have work and we have change in thermal energy. Here's another situation. Maybe this one's more believable. Okay, so do we have a change in kinetic energy inside this pot? No, right? Do we have a change in potential energy? No, we're not dropping it or putting springs on it or anything. So no change. Do we have any external work happening on our system? No, remember, work has to have some sort of displacement. Is anything being displaced? No, right? Because what would the force be? They're the force of fire. And if there's a force, even if the fire had a force, it would have to like shoot the pot up into the air for it to be considered mechanical work. It's okay, fine. It's an inductive heating. But shut up. But the total energy increases, right? You can measure there's a temperature change. So what are we missing? Well, probably heat.
An equation.
An equation.
She's like, you're right.
That's always true. We're missing some math. So remember, here's some definitions. Thermal energy is the energy of a system due to the energy of the molecules and atoms inside. So if the molecules and atoms are moving around or jiggling or whatever, that's your thermal energy. Okay? Temperature measures the thermal energy. So there's some relationship between temperature and thermal energy, but if this goes up in about the same amount. Okay? Heat is energy transferred between two objects which are at different temperatures. So if you touch the table, there's a heat transfer, and that's Q. Okay? So in terms of the kettle, when you put fire on something, that is transferring heat from the burning wood to the kettle. Okay? And it turns out there's signs for this. So if your heat's going into the system, we call that positive. So the Q for the kettle would be positive. Okay? Heat going out of the system, we call negative. So if you had, let's say you put the kettle in the freezer afterwards, then the system would have negative Q. Okay? So here, let's try that out. We're going to do this until we get 100%. Although in this class it might be easier. The other class never really got there. All right, so it's either plus or minus. All right, please discuss quickly and we'll vote again. But okay, we have 100%, but not 100% response. But that's okay. So, what's your system? Coke, right? Including the bottle. Okay. So if you put a warm Coke in the freezer, which way does the heat go? Out. So your system is the Coke. What's your environment?
The
Freezer, fridge, yeah. So if your heat is going from inside the Coke, inside the system, to outside of the system, into the environment, then your Q should be negative. Okay? Heat is leaving the system.
If you said that the system is the freezer, is that the next question? If you
No.
said the freezer is the Coke, like is the freezer and the Coke, would Q be zero because it's leaving?
Q would be 0. Yeah. If the system was the freezer and the Coke, and no heat left the freezer, entered the freezer, then Q would be 0. Yeah. So it depends on where you put your boundaries for the system. Yeah. Here's. All right. So, yeah. And somebody's going to be like, we didn't really define the system. But if your system is the Coke, Okay. Then energy, the heat is moving from the environment into the Coke, and then Q should be positive. Here's a last question. That's not even an answer. All right. Well, it's 0. All right.
The sound of defeat.
Okay.
Dude, that's
Who has that number 3? I'm not here.
Yeah.
That's awesome.
Dude, number 3.
I mean, number 2 looks like a
That's
toilet in
fancy.
county, you know?
Straight toilet seat.
Okay. Remember,
Caca particle.
we can't do this first
Minus the lid.
quietly to ourselves.
That's true. It's a jail. It's a jail toilet.
Because it fucking
Okay. Let's discuss this.
Oh, I'm the only one.
So the correct answer is C.
Yeah, I did it.
Room
No, they're all-
temperature. Okay. It's 71 degrees in here.
The third one just looks nothing.
I didn't ask like which looks most delightful. In that case, this one looks delightful, but it's gross.
I just like the vision of walking into a bathroom and seeing 3 toilets on 3 different kind of like tiles.
Okay.
Like, just
You guys got way out in the weeds on this one. If it's 62 degrees in this bathroom, what's the temperature of this toilet? 62. 62, yes.
What did the material matter though?
It does. Not for temperature. Okay? So,
Oh.
sorry, I don't know. That's just the toilet. I found that picture when I Googled this. So, heat transfer, which is heat, Q, not temperature, is what you feel. Okay? We know all of the things in this room, except for the other people, are 71 degrees. But some things feel colder when you touch them. Why? Why does metal feel colder? Yeah, it transfers heat quickly. Okay, it's a good conductor. So conductors feel colder because they're basically sucking energy out of you faster. Okay? So conductors feel colder, even if they're not at different temperature. We don't feel temperature, we feel heat. Okay? Also, heat transfer, not temperature, is what burns you. You can touch something that's really, really cold as long as it doesn't transfer heat or cold quickly. Okay? That's why you can get burned by something cold and something hot. You get burned by cold things because a lot of energy leaves your body. You get burned by hot things because energy goes into your body quickly. Okay? You can touch something really hot. If it doesn't transfer the heat to you, it's not going to burn you. All right? Which is why they let kids use these sparklers. They get really, really hot, but they have really poor heat transfer. I mean, you can still burn yourself, but it's not that.
It's one about that where it's like, I saw them do it on Netflix, where like, this guy dipped his hand in water and he tossed himself in a super hot pan.
Oh. No. If you have, that's why you can touch things with an insulator, right? If you have an oven mitt on, you can touch something really, really hot and not burn yourself because it slows down the heat transfer so much that it doesn't actually get to you and to burn you. It'll warm up, but it doesn't transfer heat fast enough to burn you. Fun fact, when I was in grad school, I was dating this guy that worked at the super low temperature lab, which is super awesome. So they had liquid nitrogen, and they also had liquid helium, but you don't want to mess with that shit. So you can put liquid nitrogen in your hand, but what do you think you have to do so you don't burn yourself? Keep it moving. You bounce it, right? So we're all sitting there bouncing liquid nitrogen because, like, we're cool. And we're, like, playing with the liquid nitrogen. And one of the postdocs comes up and she's like, oh, I want to play. And they poured liquid nitrogen in her hand and she just stared at it and burned all the skin off of her hand. And we're like, fucking theoretical physicists, man.
We were like in 4th grade and we were doing like kind of like this. We got dry ice and you put it in a glove.
Oh, yeah.
And because you tie it off and the gas is bad.
Oh, yeah.
And when he was fucking holding it like this and it burned through the glove into his hand and he like freaked out and it wouldn't like leave his hand.
Yeah.
They were like, yeah, you're fine. Like, you can go home.
Yeah, the main disappointing thing about this was this person had a PhD in physics and still burned themselves on liquid nitrogen. Turns out smart and smart are different. SMRT. Okay, so anyway, here's our equation from before. Here's our thermal energy, change in kinetic energy, change in potential energy. We don't worry about so much when we're talking about thermodynamics. Here's work done on the system by the environment, so any external forces coming in. But we have to add one more thing, and it's heat. Okay, this is heat transferred into the system. All right, and if it gets transferred out, what do you do with this? Negative Q. Okay? So once we get rid of those things, we call this the first law of thermodynamics, which is not, don't tell people about thermodynamics. It's just this. So the first law of thermodynamics is thermal energy is heat plus work. Okay? So work done on the system by the environment, heat transferred into the system, and change in thermal energy. This is the first law of thermodynamics. All right? You guys want to go home? And this is our first law of thermodynamics. Okay? That's the first law. And that's where we left off. Did we do this slide? Have we done this one? We did this one? Okay. So let's move forward to heat transfer and temperature change. Okay? So if we're doing heat transfer and temperature change, we're not using any external work, right? We're not applying any physical forces to our thing, just microscopic stuff. And perhaps you've seen this. Anyone? This look familiar? Yeah, this looks like chemistry. That's okay. It turns out that chemistry is just applied physics, so whatever. Temperature change, heat transfer. What's this M? Mass, okay. And then what's C? Specific heat. Okay, so specific heat tells you about how much energy it takes to raise 1 kilogram by 1 degree Kelvin. Okay, so how much heat do you have to put in to raise the temperature 1 degree for a certain amount of a substance? All right, and here's some standard C's, right? These are specific heats. So we have aluminum, copper, gold, lead, ice, and then for some liquids we have alcohol, mercury, and water. Okay? Now what does it mean if something has a really low specific heat? So like which one of those things would make a really good frying pan? Do you want the number to be higher or lower? Lower, right? Why? Yeah, it heats up faster because it takes less energy to change the temperature. Okay? So it takes less energy to change the temperature 1 degree. So what's most of our cookware made out of? What are your pots and pans made out of? Aluminum, okay? Copper. Kat, if you have like a skillet, right? Like a cast iron, that's iron, right? So people always that like to cook rave about cast iron skillets. So if you read stupid food blogs, why you can see that gold and lead have much lower heat capacities. Why do we not make cookware out of, let's say, gold? Well, lead is poison, so that's why we don't use lead. And gold is too expensive. Also, it's not very durable. Like if you make your cookware out of solid gold and you like drop it, it's going to dent. It's very soft, okay? So you probably have it would be nice, you have little flecks of gold in your food because the gold doesn't stay together that well, but it's not really a cost-effective way to do things. Now, if you have the means, copper and iron are pretty good, but aluminum works too, okay? The professional says no. Okay, apparently you're all cooking wrong. So yeah, that's what specific heat is. All right, that tells you how much energy you need to change something's temperature. All right, so we're going to do this quick and really easy example. So how much heat is required to raise the temperature of 3 kilograms of aluminum from 20 degrees to 30 degrees Celsius? Okay, so we use this formula, Q is equal to mc delta T. All right, and we just want to find Q. So what's our mass?
3 kilograms.
Yeah, 3 kilograms. We're given our specific heat of aluminum. It's 900 joules, kilograms, Kelvin. And then we have 20 to 30 degrees. So what is delta T? 10.
Should be the kilos, right?
So here's the thing. Does it matter if we convert if we're subtracting them?
No.
So if you can, right, if you do 30 minus 20, you get 10 degrees, okay? Let's say we convert this to Kelvin. That's 293 Kelvin and 303 Kelvin. 303 minus 293, also 10. So if you're subtracting temperatures, you don't actually have to convert to Kelvin, okay? 10 degrees Celsius is the same difference, literally, as 10 degrees Kelvin if you have a difference in temperature. If you're using a temperature value like just plugging in temperature, just one temperature and not taking a difference in temperature, then it's really important that you use the correct one. Okay? So if an equation has T in it, use Kelvin. If it has delta T in it, Kelvin or Celsius are fine. Okay? So, 10 Kelvin. And why do I write it in Kelvin if I didn't convert it?
Cancel.
We know it's the same and we need it to cancel, right? So if you look at the units here, this thing looks like it has dumb units, but it's because they have to cancel to give us joules. Okay? And so that's going to give us about 27,000. So 27 kilojoules. Okay? 27 kilojoules. This is just a plug-in formula, but I want to do this kind of problem because I want you to see how the units work and how to deal with temperature. Okay? All right. Oh, Q equals MC delta T. Here's another thing I want you to think about. You can see sometimes I get bored and I make too many animations. If we don't have any external work, what is this also equal to? Thermal energy, right? And remember I told you thermal energy is proportional to delta T. So if this is also equal to thermal energy because of the first law of thermodynamics, okay, that means thermal energy is proportional to T. What's this? If you graphed it, what would that be? The slope, okay? And it's a constant slope because remember M is constant. Okay, it's just how much of the substance you have. And C is a constant, all right? So that's what I mean when I say these two things are linearly related. You can also get the literal relationship between them, okay? As a side note, there's also molar heat capacity, and really this matters if you can rewrite this equation so that you get the same thing, but you use moles, which is sometimes useful if things are small. Okay, so you can convert this back and forth between moles or mass. We're not going to use moles very much here, but I just want you to know that you can do that because I think that's how it shows up in chemistry. I don't know. It's been a long time since I took chemistry. So yeah, it turns out this is the molar mass. This is just a side note. You don't have to know this for a test or anything. This is the mass. This is the number of moles. You multiply those together, you get the actual mass. Okay, and there's these tables for molar heat capacity. And so, but what we are going to see later is we have something that looks like this, which is Q is equal to NC delta T. When we start talking about gases and we do like PV equals nRT stuff, sometimes we're given moles, and then you just need the molar heat capacity, or you have to convert to mass. Okay, and so depending on like what we're doing, these two equations are equivalent, but they have different applications. Okay, and these are just, this is the specific heat, This is the molar mass, this is the molar heat capacity. It's easy to go back and forth. It's just two ways of doing the same thing. All right? And here's where it's going to come in later. You will see these things again. So what? Well, this is called a PV diagram. Okay? This, what's the P stand for? Pressure. What's the V stand for? Volume. And then you have these temperature lines. These are called isotherms. That means it's a line of constant temperature. Okay? How would you find a line of constant pressure? What would it look like? Yeah, horizontal, right? Anything along this line has pressure P1. All right, the volume's changing, the temperature's changing, but the pressure's not changing. Okay? Any vertical lines, these are constant volume lines because anything along this line has volume V1. Anything along this line has volume V2. Okay? So you can have constant pressure, constant volume. You can also have constant temperature. That's a little more difficult because you have to know where these lines are. But if you follow one of these lines, if this is 10 Kelvin, and this is 10 Kelvin, and this is 10 Kelvin, and this is 10 Kelvin, anywhere along the line you have the same temperature. Okay? So we're going to later deal a lot with PV diagrams, and we'll draw these little charts. So these are states. Okay? And what I mean by a state is a state has a particular pressure, volume, and temperature. Okay? And you can change states. And the way you get to a state matters because you can go through this process to get to this one, or you can go through. So basically, let's say this is 50 Kelvin and this is 100 Kelvin. All right, so you can change temperature. Both of these have a temperature difference of what? 50 Kelvin. Okay, so if you go this way, your temperature change is 50 Kelvin, and if you go this way, your temperature change is also 50 Kelvin. Okay? But you've gone a different path. One way, you've gone the same temperature change, but you kept the same volume. The other way, you have the same temperature changed, but you didn't change the pressure. Okay? So one of them, you're either you're adding more pressure. So like, let's say you put this in some sort of pressure cooker, but you kept the volume constant. Okay? In this case, you've kept the pressure constant, right? But you've changed the volume. Okay, there's different ways we can go about this. We'll talk about this in more detail later. But the end result is you have the same delta T. Turns out these things give you different amounts of heat. Okay, the process you use matters when you're talking about gases. So we have two different types of heat capacity. One for constant volume and one for constant pressure. Okay? And these we'll talk about in more detail later, but I just want to mention them while we're talking about the standard Q equals MC delta T. Okay? And the nice thing about the Q equals MC delta T is it's generally true for solids, liquids, and gases. This is something that really only comes up when you get to the gas state, and it's only really true for an ideal gas. Okay? And we'll